Hello everyone, hope you and your family members are in good health in this crisis period of both Corona and Amphan. So I have heard news from all around. I have got WhatsApp messages from you that you don't have electricity, network connection, everything in your area or locality. I don't know when everything's gonna be all right, but we just have to wait and hope for the best situation. So today I'm going to take a class on quantum mechanics, and I will start from where I left in my earlier class, which was on Compton effect, I think. So for time being, you just wait when everything comes under control and you get access to this video and the network. So don't panic till then. So we are going to start our class today. Okay, I think you can watch this. Okay, so I can, you think, watch this PDFs. So it has already been shared with you through Google Classroom as well as my WhatsApp group. And I hope that you have read some portion of it because you have already given one exam on this topic. But someone told me that they were having some difficulties in understanding the topics. That is why I made this video. So those who have missed the online classes, it will be helpful for them also. So while considering the Compton effect, it was assumed that light was behaving like a particle which was named as photon particle. For pair production or photoelectric effects also, it is seen that light behaves like a particle, which means that it has a dual nature. So it behaves as waves for sometimes it behaves as particle. And when it behaves as waves, so when we consider the phenomena of interference, diffraction or polarization, we see that light is behaving like a wave. And when we consider the phenomena like photoelectric effect, Compton effect, Raman effect, everything, all these effects, they can be explained with the particle property of light, which means that when light propagates from one position to another position, it propagates as a wave. But when it interacts with matter, it behaves like a particle. So it has a dual nature. And according to quantum theory of radiation, a photon particle has a relativistic mass of h nu by c square, velocity c, and momentum h nu by c. Now, this is confirmed as light. This is confirmed that light has a dual nature, both wave and particle. Now, by the analogy, we can also say that matter can also behave like wave sometimes. That was proposed by de Broglie. His hypothesis was there is always a wave associated with every moving particle, and the corresponding wavelength is given by lambda equals to h by p, where p being the momentum of the particle. So de Broglie suggested that particles or matters also have some wave property. They also behave like wave, and the wavelength is given by lambda equals to h by p, where h is the Planck's constant and p is the momentum of that body. Now, from where did he got this formula? For this, he followed the photons formula, because for a photon, the energy is given by E equal to h nu. And for a relativistic particle, we know this relation E square equal to P square C square plus M0 square C to the power 4. Now for a photon, M0, the rest mass is given by 0. So E reduces to E equal to Pc equal to h nu, or P equal to h by lambda, or lambda equals to h by P. So this relation holds good, or it is true for a photon. De Broglie assumed that this relation has to hold good for matters also. For example, the next example is the de Broglie wavelength of an electron. So he assumed that the relation should hold good for subatomic particles or elementary particles like electron, proton, and everything. So now we are going to find out what is the de Broglie wavelength of an electron. So consider an electron of mass m, charge E, and it is subjected to a potential difference capital V, so that it acquires a velocity small v. Then its kinetic energy will be given by capital E equals to half mv square equals to E into V, where this V is the voltage capital V and the small v is the velocity of the electron. So what is the relation of velocity v and the voltage? So it is given by v equals to root over 2 ev by m, or we can write it root over 2 e by m, where capital E is the kinetic energy of the electron. So v is given by this. So lambda will be given by h by mv. Put the value of v and you will get it is equal to h by root over 2 mev, where E is the charge of the electron, m is the mass of the electron, and capital V is the voltage difference along which it has been accelerated. And if you write it in terms of only energy, kinetic energy, then you can write it h by root over 2 me. Now look at the equation. Here h is a constant, m is also a constant, the mass of electron, charge is also constant. So everything is depend on the potential difference V. So if you put those values, numerical values of h, m and E, and calculate it, you will get lambda is given by 12.26 divided by root V angstrom, where V will be in volts. So if you are given a problem where you are told that an electron is accelerated under the potential difference capital V equals to 10 volt, what will be the de Broglie wavelength corresponding to that electron? What will you do? You just put capital V equals to 10 in this equation and you get the wavelength of that particular electron in angstroms. Okay. Now we come to proof of matter wave, which is the Davison-Germer experiment. Now, in science, a theory is only a theory till it is proved by experiment. So, everybody obeys or everybody accepts the theory only when it is experimentally proved. So, the theory of de Broglie, which is lambda equals to h by p, it was first experimentally proven by Davison and Germer. They did some experiment and they proved the theory. Now what or how did they do it? For that we first need to know the experimental setup of Davison and Germer experiment. So look here in the picture, the experimental setup is drawn. So this one is F. F is the tungsten filament from where highly energized or energetic electrons, they come out. And the A is an anode. Actually these are used to collimate the electron beam so that a small ray of electron, it comes through the hole H. Now here a block is, you can see it is a nickel crystal is given here. The electrons, the ray of electrons, not the ray of electrons, the electron beam, it actually falls on this nickel crystal and the electrons get scattered by that nickel crystal. So it gets scattered at different angles. Now here we have kept a Faraday cup named C. So C is actually the electron detector which collects the electron and converts them to current, and we measure the current through this galvanometer connected with it. So the number of or the amount of current will tell us actually the number of electrons. The more the number of electrons captured by C, the more will be the amount of current in the galvanometer G. So we have kept C here, and it can rotate around this dot dot line. So the cup can rotate. So what is happening? Electron beam falls on the nickel crystal, and it is getting, or they are getting scattered at different directions with different scattering angle theta, and the electron gun, it is rotating and it is capturing those electrons at different angles. Now they did this experiment for various voltage differences between the cathode and anode, as well as various angles of scattering. And what did they find? Now, depending on the various voltage differences, the electrons will have different energies, as well as their de Broglie wavelengths will also be different. So now we are going to find out the experimental results, then we will analyze the result. So what was the experimental result? So for different values of accelerating potential V, the variation of current versus theta is plotted in a polar graph. Now, you have seen Cartesian graphs, but what do you mean by a polar graph? Polar graph means something where, suppose you are plotting intensity versus some angle, or the current versus some angle. So if the current is same for every angle, then in a polar graph, you should get one circle, because the intensity or the current, it will be proportional to the radial distance of the point. Now look at this picture. So radial distance means distance of any point from the origin. So if you take this point, so here the current will be proportional to this distance, this point to origin, this distance. If you take this point, the peak one, it means that here the current is proportional to this distance, this dot dot line. So where the current is greater? Obviously at the sharp edges or kinks, because along any circle in a radial graph, the current will be same for every point, because the radius is same for every point on a circle. But if we get a kink in any circle, that means there is some peak of the current. Likewise, in these pictures, here we see that for 44 volt energy, or for 44 volt voltage potential difference, we get a sharp edge or a kink at 60-degree angle. That means when the potential difference is 44 volt, we get maximum amount of electrons are being scattered at 60 degree. Similarly, when we increase the voltage a little bit step by step, and we see that the graph changes at V equals to 54 volt, we get the highest amount of current at the angle 50 degree. So it is the maximum for the whole experiment. Now again you move on and increase the voltage. For 48 degree, the graph is like this. So here we also a small kink at 40 degree, but it is less than that the previous one, which was at 50 degree and it was for 54 volt. So for 54 volt and for 54 volt, we get the highest amount of scattered electrons at 50 degree. Now, let us calculate the de Broglie wavelength of electrons at 54 voltage potential difference. So what will be the wavelength? You just put on 54 in the place of V in this equation, because you have already done it in the previous note, that lambda is given by 12.26 divided by root V angstrom. Put V equals to 54 volt, you will get lambda equals to 1.66 angstrom. So theoretically, the electrons should have this de Broglie wavelength, lambda equals to 1.66 angstrom. Now we get one thing. Now what do we get experimentally? Experimentally, we are getting a kink at 50 degree. So let us check. Now you have heard of X-ray diffraction or Bragg's law in X-ray diffraction, which states that 2D shine psi equals to lambda, where capital D gives you the interplanar spacing between two consecutive planes, and psi gives you the glancing angle, which is the angle between the plane, that is angle between the plane and the angle of, sorry, and the incident ray. So 2D shine psi equals to lambda. Now look at the picture very carefully. If this is the angle psi, then angle phi will be 90 degree minus psi, where phi is the angle of incidence. Now we see that the scattering is happening at angle 50 degree, which means that this angle will be actually theta. I have not drawn it. So theta will be basically 2 into phi. So this angle, this one I am marking by this arrow, this angle will be the scattering angle theta, which will be given by 2 into phi. Psi is the glancing angle. So 2D sin psi equal to lambda gives you 2D cos phi equals to lambda. Now what is D? Capital D is the interplanar spacing between the 111 planes of the nickel crystal. So I have enlarged the picture and drawn it here again. So this AC distance is actually capital D, the interplanar spacing. And what is the relation between AB and AC? AB is given by, sorry, D is given by small d into sine phi. If this is the angle phi, then angle CAB will be 90 degree minus phi, and angle ABC will be phi. Okay, so angle ABC is phi, AC is capital D, and AB is small d. So what is the relation of capital D and small d? Capital D is given by small d into sine phi, where small d gives you the spacing between the atoms in the nickel crystal at the horizontal level. Okay, so if you put these values in this equation, you get 2d sine phi into cos phi is lambda, or small d sine theta equals to lambda, where theta is the angle of scattering. And if you put for the 1 plane of nickel, small d equals to 2.15 angstrom and theta equals to 50 degree. If you put this in this equation, you get lambda equals to 1.65 angstrom. Now, this relation holds good for an electromagnetic wave, because we have assumed X-ray diffraction, right? So if we assume a wave is being scattered by the nickel crystal at an angle 50 degree, we see that its wavelength has to be 1.65 angstrom. And what is scattered? What is being scattered from there? Electrons. According to de Broglie's theory, the electrons should also have the wavelength lambda equals to 1.66 angstrom. Look at the results. They are almost equal. So this is the proof that de Broglie's theory was right. Matter waves really do exist. So Davison and Germer proved that de Broglie's law, or sorry, Bragg's law is valid for electrons also. So electrons also behaves like waves. So we get an experimental proof. Okay, so this was Davison's and Germer's experiment to prove de Broglie's theory of matter waves. Now, what do you mean by matter waves? So I am stopping right here. In the next class, I will wrap up the whole thing because I think I don't have too much time. Okay. Thank you.